Okay, my name is Seppo Korpela. I was a professor of mechanical engineering, specialized in energy subjects at Ohio State University for 40 years, now retired. And I'd like to talk about end of declining era of declining fossil fuels. I've been talking about this stuff for about the last 25 years, and looks like we are getting close to where we're going to be in real trouble with regarding fossil fuels. But before launching into that topic, and I'll concentrate mostly on oil, let's talk about primary energy consumption. By the way, I gave this talk, this kind of talk, it's on my YouTube channel in 3 years ago, and there's some repetition of this stuff here, but there's a lot of new stuff too. Uh, Primary energy comes from various sources. As you can see, what is colored here, most of it is originally traditional biomass, then came coal, oil, and natural gas. They comprise about 89.1% of primary energy consumption. Early going, we had only biomass. Then the steam engine was developed, and great by Savory and Newcomen. Then James Watt in 1776 improved it greatly by separating the boiler from the condenser, and the efficiency went up. And then the steam engine got various uses, including for locomotives and so on, and not only as a prime mover to pull belts in factories and whatnot. And the coal consumption started to increase. Well, then at the beginning of last century, yeah, the car industry was born, car was developed, and it started consuming a lot of petroleum. Today, there are around 1.4 billion cars and light trucks in the world, and they do require a tremendous amount of oil to keep them going. Then the middle of last century, the natural gas, we started developing those resources. And of course, natural gas is used a lot in chemical industry. It's used to make fertilizer, heating houses, and so on. So, as I said, these three fossil fuels are our main fuel source in the world. Since 1960, I've taken this as a reference year. So we are now at about 64 years into the future. And if you go other 64 years, we are at close to 2090, 2088. Now, we have been increasing consumption at about 1.7% a year. Now, all non-renewable energy, primary energy sources, they undergo a bell-shaped curve. And we are now on the kind of the rising side of the bell shape, and I claim that we are hitting a peak and we're going to start coming down. And that is basically where the trouble starts for societies around the world. This is also true for things like primary metals, so that they also go this kind of a bell-shaped curve. Now, if you look at what happened in 1960 versus 2023, here are some data. The coal, oil, and gas was 76.3%. Coal, oil, and gas today is 89.1%. There's a mistake in the slide. And then earlier, there were no nuclear, wind, or solar to speak of. Hydro was 4.5%, and biomass was still around 20%. Today, these wind, solar, and others include modern biomass, a little bit of tidal power, not much, geothermal, and so on. And we are at 3.5% together, wind, solar, and the others. So no other source has increased beyond 5% than the three fossil fuels. Now, I'll next talk about oil depletion, past and future. And there are two approaches to it. I will not talk very much about this bottom-up analysis. I'll concentrate on the logistics and Hubbard's analysis. But if you, the bottom-up analysis have been done by two groups, Uppsala Hydrocarbon Group and United States Geological Survey. And basically what they looked at all the oil fields in the world, what was happening to them. One conclusion which from that study came that, that about half of the world's oil comes from 1% of the fields in the world. So we're depending on these very, very large fields, and that is what's powering this world. Now, the London Bank, HSBC, issued a report in 2016. RISU was based on these fundamental studies, and they concluded or pulled together threads and noticed that 81% of the production is in decline. Decline rate of 2016 was around 5 to 7%. I think one can safely say it's probably around 7% today, this many years later. And so we are losing around 4 million barrels a day production every year. And that means that we have to replace 4 times the Saudi Arabia's production in order to stay flat. So we talk about 40 million barrels because that's what Saudi Arabia is producing, around 10 million barrels a day. And then they noticed that the world depends increasingly on smaller fields of the size of 75 million barrels. And I will show you that we are using today about 84 million barrels a day. So these fields are just one day's supply, each one of them. And then the exploration rate was also very, very low. And in 2050, the average field size, discovery size, was only 24 million barrels. Now let's move to this Hubbard's logistic model. It's given here. I'll put these equations here so that the younger people can stop the slide and copy them down and do it as a homework, see what they can get out of them. But in any case, they are simple first-order differential equations. Capital Q is a cumulative production. So we have a dq. If dq is a yearly production and dt is 1 year, so the ratio dq dt is 1 yearly production. I've denoted it on a low here with a small q. So what we have here is that the yearly production is some function of the cumulative production. So cumulative production, of course, is that you take a yearly productions and you sum them up from beginning to the today, and you get the cumulative production. Now, if you look at that equation, you can see that when the capital Q, cumulative production, is equal to Q0, the right-hand side of the equation is 0. That means that we are at the end of the oil production, and Q0 is then denoted as ultimate production. The other thing you notice that in the very beginning, dq dt is 0 when capital Q is 0. So that is the beginning of oil production. Then if you, at the beginning also, capital Q is much smaller than Q0, so you can neglect the second term, and what you get is an equation which represents exponential growth. Then if you recast this equation in terms of the remaining oil, QR is Q0 minus Q, you get the same equation except with a minus sign. At the end of the oil production, capital QR is much smaller than Q0. So you again neglect the second term, you're left with the equation which shows an exponential decay. So A is the initial growth rate and the final decay rate. This is a physical meaning of these two important parameters in here. Now, you can also note that if you plot the right-hand side, that is a second-order equation. It's a parabola. It cuts across the horizontal axis at Q equal to 0, capital Q equals 0, and capital Q equal to Q0. And it rises to a maximum at the midpoint. So that's where the capital Q is 1/2 Q0, okay? And if you substitute that one into this equation, you get that the maximum yearly rate is AQ0 divided by 4, okay? So that's much about the equations without having to solve them. Now, if you solve them, this is what you get. The cumulative production is given by this expression, then yearly production next. And then I also developed this equation for fractional growth and decay at the how it behaves. Now, there's an integration constant which comes out of this integration. I call it T sub P. And you notice that when the year T is equal to TP, the hyperbolic tangent is equal to 0, and capital Q is equal to 1/2 Q0. Well, I just said that that is represents the peak production rate when that takes place. So that means that the year TP is the peak year. Okay. So then let's plot these graphs. And we have the top left, we have the yearly production, this bell-shaped curve, which I mentioned. Then we have this next one, which is a straight line, because if you divide that equation by capital Q, you get a equation for a straight line. It cuts across the horizontal axis, where Q is equal to Q0, and it cuts across the vertical axis, where Q divided by small q divided by Q is equal to A. You can see that from the equations. Then we get this bottom left sigmoidal shaped curve for the cumulative production, and then this fractional growth and decline is given by this kind of a shape. Is actually also a hyperbolic tangent, but it starts from like 5% growth in the beginning and 5% decline in the end for the data which are used to generate this graph. Now let's put the actual data in for the world's oil production, and you notice that in the very beginning it is quite scattered, but then it starts to follow a kind of a straight line. I took the 1994 as the beginning year and fitted a linear fit for the data with the least squares technique, and I get the middle line, and then the sidelines are their 95% confidence intervals for that all the data will fall into this band. And what you get out of that, it cuts across the horizontal line at around 2,800 billion barrels. So that is the ultimate production. And then it cuts across the vertical axis at around 4%. So those are the two parameters for the world's oil. And you can kind of see what happens to other things when we go along. So now we look at the yearly production, and this is given here. I also have the monthly production superimposed in here with a kind of a purple crosses out here. So now it shows that we actually passed peak production. Now people have criticized this method for a few reasons. One is that well, it's a symmetric. The underlying curve is symmetric. But we are not trying to fit the data into the symmetric pattern. We are looking into the future, and the past data is past, and we'll just plot that thing in and try to see what the future, how well we can predict the future with this method. So we can dispense with that criticism very simply. Now, the second criticism is that, this method is too simple. That maybe we should use some kind of an econometric model, but the trouble with the econometric models are that there are a lot of parameters in there, and there's difficult to figure out a rational way to estimate the value of these parameters. The beauty of this one is the simplicity and the fact that there are only two parameters in this model, and I've just shown you how you can get it for a large region like the entire world. Okay. Now, so I don't buy this argument that this is too simple model. In fact, it is its virtue. The second thing is that they say, well, it doesn't take price into account. Okay. Well, it turns out that if you look at the past data, it took every possible thing into account because which might have influenced the oil production in the past and the present year, maybe with a lag. But that one also is a kind of a specious argument that it doesn't take these things into account. It takes them account implicitly, not explicitly, however. And notice that the COVID drop year 2001, this one, of course, nobody could predict, but it's now in the past, and it shows up in the data, of course, not in the model. Now, there's one serious criticism of this method is the following, is that as you keep adding new years in and redoing the calculation each year going forward, one notices that the peak keeps drifting into the future. So they say that, okay, we have to reject this model because it's not very robust. Well, I've been doing this stuff now for over 25 years. And already in 2002, I noticed this fact that it moves into the future. And the way to take care of it is that you plot the year of prediction made, and then on the vertical, you plot the predicted peak production year. And this is what you get. So in year 2000, you are predicting that the peak will take place in 2617. So that was 17 years in the future. And then as you move along, you notice that the gap narrows between the prediction year, the year prediction was made and the predicted year until you move to the right side of that bisector there. And that means that the peak is in the past. In fact, as the previous slide showed, and this one confirms it, that the peak year was already, or peak month was November 2018. So we are couple of months into past the peak production already. So I think I've taken care of these objections to the model, and I think that I trust that it is going to predict pretty well what's going on in the future. So now let's look at where the world's oil comes from, or where it comes from. Well, if you look at the top line, that's the world production, and I'm also considering here only considering crude oil and condensate. There's a component called the natural gas liquids, which comes from the natural gas plants. And if you include that into this thing, this would come to about 100 million barrels a day for the world's production. I'd ignore that because that one goes to the chemical industry, and I'm mainly interested in what happens to the transportation fuels and the big machines which we use to move mountains and farm machinery and so on. So I'll forget about the natural gas liquids. Now, if you then take the world minus USA, Saudi Arabia, and Russia, you notice that it's been basically flat for about 20 years. Okay, and then if you look at the rice and you look at the US rice, most of the rice for the world has come from the United States. Well, it's a result of this fracking technology, which started around 2006 and have accelerated since that time. And about 80 to 90% of the world production increase can be accounted for the increase in the US production. Okay, then let's move to OPEC production. Well, OPEC now has changed actually who are actually member. They are now OPEC Plus, and originally they were like what I call here are the seven miners, which are kind of don't produce that much, and then there are the four majors or five majors: Saudi Arabia, Kuwait, the Persian Gulf countries, Saudi Arabia, Kuwait, Iran, Iraq, and United Arab Emirates. So there are five. And these other ones, you notice that most of these are actually in Africa. Venezuela, of course, is in South America. But anyway, these miners, you notice that the production has dropped from somewhere around 97, 98 until today. And the brown graph is the logistic method trying to predict where we are heading in there. But if you have regions or countries, larger regions, where you already passed peak production and you're going downhill, there's another way to analyze this data. And what you can do is if you assume that the decline is exponential, then of yearly production, then you can show by plugging in the exponential decay in there that the yearly production, I mean the cumulative production, behaves in the following way. That is, it's really proportional to the yearly production is proportional to the remaining oil, cumulative remaining oil which is left. Though on the bottom, we have that graph where the yearly production is minus lambda times QT. So if you plot the Q on the vertical axis, small q, and the capital Q on the horizontal axis, there's a slow line which is slope of minus lambda, where you can pick up how it behaves. Well, if you apply this thing to these OPEC minor producers, you get a graph which looks like it's starting to follow a kind of straight line down. And you can see there, about 20 years you had dropped that much, and another 20 years you are basically close to zero in the production for them. Actually, they are not going to go close to zero, and I want to talk about that thing a little bit more, because when the countries start depleting their resources, they don't export anymore, and they start using all the oil for their own purposes. And that is another issue which is worthwhile to remember. Now, if you then go to take all the OPEC countries and plot these things in, you get a straight line like this, again from starting from 94. And now there's a little bit more scatter in there because it's a smaller quantity of oil we are dealing with. The larger the region you're studying, the tighter the fit is. But nevertheless, I suspect that we are going to follow that line going forward here. It shows that the the ultimate production here is 982 billion barrels. But if you look at the official statistics, OPEC claims that they have reserves of 1,237 billion barrels. So we have about 300 billion extra in here. And I'll show you why that is probably kind of a false reporting. So now if you put this quadratic, the logistic fit into this OPEC data, you can see the brown graph, how it behaves, and the blue ones are, of course, the data. And it looks to me that OPEC has also gone over peak production. But time will tell. A couple of more years, and we'll know that for sure. Now, then, if you look at Saudi Arabia in particular, and you try to apply the same method, again, we have a little bit trouble because the data is more scattered, and the question is, what is a good line to fit through it? But my best ability, I've drawn this kind of a line. And that gives you that the Saudi Arabia's URR is the ultimate recoverable reserve. That is the Q0. I call it other place Q0. That to be 340 billion barrels. Now, Saudi Arabia's reserves are 291, but the actual should be the cumulative from this deducted from 340. It should be only 180. Okay. So now, if you look at the Saudi Arabia's production and then this logistic fit through the data, this is the kind of result you get. Let's see if this one is going to be true. I'll give you some more results from Saudi Arabia just now. Namely, okay, I want to go talk about this one first. That if you look at the Saudi Arabia's fields, okay, here's a graph which these two Frenchmen, they got access to Rystad's energy database, and they dug up some data from there and plotted this way. And the horizontal line is the year when the production started, and the vertical line is the delay from the discovery year to the year first oil production. So earlier, the delay was something like 10 years, 10 to 15 years. But then when you move to the right corner here, you can see that that there's a very large delay. Some of these fields were discovered 40 and even 60 years ago. Well, why is that so? Well, okay, Saudi Arabia had plenty of good fields to produce in the early going, and they didn't need these large fields which they discovered already that time, and they left them unproducing. Perhaps another reason was that if the geology in them was quite difficult, so that the oil was hard to produce, it would make sense to leave them and until technology develops and they can develop them later. Now, if you look at this graph, what has happened also when you look at the discovery, and this is average field size based on the logarithmic vertical axis, which means that across every square, the field size increases tenfold. And what you see is, of course, the 1951 field is the largest field in the world, the Ghawar field of Saudi Arabia. The one before that is the second largest, the Safania field, which is on the Gulf of Mexico, Gulf of Persian Gulf. That is, of course, the largest field offshore. And then there are these various other fields. But then when you come towards the right edge of the curve, you can see that there's this bunch of fields, I don't know, 20 or so, where the field size is only 100 million barrels. And 100 million barrels is basically how much you use every day. So these fields, which are on the right-hand side, they don't amount to much. I mean, a couple of months production at the best. So that underscores the idea that all this stuff comes from a very, very old fields. Now, this graph shows, they also constructed these graphs. It's an attempt to find out where this oil comes from, which fields. And you can see the fields from 1940, they were the mainstay for a very long time. And now they are decreasing. And then comes the 1950s fields, and they seem to carry an increasing burden on Saudi Arabia. The 40s fields for 4.1 million barrels a day, the 50s are 2.4, and then the 60s are 2.1. And now add them up, you get 8.6 million. Well, Saudi Arabia is producing a little over 9 million today. But the remarkable thing about this data is that when you look at what is produced from fields discovered after 1970, it's a very, very small fraction. In 1970, that was already, 55 years ago. So we're not finding, they're not producing from the new fields at all, based on this kind of a thing. So now I wanted to move to discussing exporters. There are some 65 countries in the world which produce oil. Now, out of those, 41 countries produce over 100,000 barrels a day. So the rest of them are very small producers, and they probably use them all for domestic purposes. Now, out of the 41, even those, half of them, 20 of them are producing, but using all of them for domestic purposes, because we are left with 21 oil exporting countries. Out of those, 39 decline already. So what we are left? We are left with these countries here, which I've shown here: Canada, Iraq, Kazakhstan, Oman, Russia, Saudi Arabia, United Arab Emirates, and Guyana. Okay, out of those, Canada can increase its production, but Canada's oil is tar sands from Alberta. It's heavy oil, and it's very difficult to increase the production fast. Iraq can certainly increase production. That's in fact still the main prospective area in the world. Kazakhstan production is likely to increase after this war with Ukraine is over. However, Oman's production, I think it looks like it's staying fairly flat. Russia's production was also flat already before the war with Ukraine was started. I mentioned we're talking about Ukraine's war, of course, stopping. And then I've demonstrated that the Saudi Arabia's production appears to be also basically flat. Then the United Arab Emirates, they can certainly increase oil production together with Iraq. Those are the two countries where the future oil production is able to increase. Now, Guyana, I put that thing also here because there was a recent discovery in southern part of Gulf of Mexico on the north coast of South America, where Guyana is located. And they're already producing 0.25 million barrels per day. And you notice that, I mean, they're exporting that much and they're producing a quarter million barrels a day. Well, of course, the domestic consumption is more. I could add here also Argentina, because Argentina, there's a new region there, this Vaca Muerta, where they are developing this fracking technology, or they're producing oil with this fracking technology, like in the United States. And it looks to me that they can grow. They are exporting now about 250,000 barrels, and the domestic consumption is about a little over 1 million in Argentina. Well, then, if you look at these countries which are in decline, you can see here what the situation there was. There's already 30% drop from 6 million barrels a day between 2008 and 2022. Okay. And it looks to me that this is going to keep increasing. Now, let's then talk about reserves. When you look at this graph of these reserves, then, when you casually glance at it, you say, well, look, in 1980, we had about 700 billion barrels, and today it has increased to about 1,700 billion barrels. And the question is, well, what's the problem? We are developing more reserves as we go along in time. However, there are three important things in here. There's the OPEC spurious reserve additions in the late 80s. Canadian tar sands were included into these statistics in the early 2000s or late 1990s. And then the Venezuelan oil, heavy oil, was included in here just before 2010. So, as I said earlier, these last two categories, they are slow to produce. There's a field in California, I think it's Kern River, I think, if you remember, that has been producing heavy oil for over 100 years already. Now, there are other factors, of course, that the technologies has improved greatly. Particularly, we have developed the horizontal drilling. We have the seismic technology and processing that with the new computers. Computer power has increased tremendously. And the oil industry has developed reservoir simulation models where they can track basically where the oil is going and so forth. So those are technological improvements which have allowed for the reserves to increase. But so there are two factors why they have increased. Now, the question, how far can the technology go? The difficulty is that this oil is in these very small pores. They are about the size of a pinhead, and the surface tension is there, and it's very difficult to move fluids through this kind of structure where the pore size is very small and the connections are very narrow. So this is the issue of porosity and permeability of the field. Okay, now let's go to look at these reserve additions and what I call the spurious OPEC reserve additions. Well, in the late 1980s, OPEC decided that they're going to change the way in which they assign quotas for the member countries. And they decided to partially base it on the size of the reserves. Well, the upshot was that every country increased their reserves. United Arab Emirates tripled their reserves, Iran doubled it, and so on. Same for Iraq and so on. Notice a Saudi neutral zone, NZ, nothing happened there because the additions were done by Kuwait and Saudi Arabia separately. So there is about 376 billion barrels extra in here, which I mentioned that we could take out not only, well, from the reserve additions and part of them from the OPEC's reserves. Then let's see how much oil we are finding every year. Well, if you look at year 2018, which you can see here on the bottom right, that year we found 10 billion oil equivalents. That means both oil and natural gas. You convert the natural gas to oil equivalent based on the heating value of natural gas and oil. And you can see from there, there's a gas to liquid ratio. So in 2018, 44% of this 10 billion were gas, 56% were oil. So that means that we discovered 5.6 billion barrels of oil that year. Now, we use in the world 1 billion barrels every 12 days. So that amounts to 5 billion barrels in 2 months. Okay, so we found about 2 months supply that year, 2018, as a similar thing in the various years recently. So what we are doing is that we are getting the 10-year supply, 10-month supply every year from these old fields and not from the new ones which we are discovering. By the way, we see this Guyana discovery in this green here in the insert, and that says that it has about 2 billion barrels, but I think that there's going to be more than that as the field gets developed more and more. This is more recent data, and this is also from Rystad's energy database. This shows a half a year's discoveries in these various years. So you can double that. So again, we are 2023. We have discovered 4 billion barrels of oil. Okay, so that's just shy of that 2 month supply. Now let's move then to U.S. oil production. And this is, of course, very interesting here because when you look at this figure, you can see that we can separate the United States into 4 different regions. We have the lower 48 states on the blue, then we have Alaska on the brown, and then the yellow is the Gulf of Mexico, and then we have this light tight oil which comes from this Permian Basin and the various basins around the country, which is the obtained by this fracking technology. Now you notice that the lower 48 is in decline, and you can look at the band for Alaska, and that is also clearly in decline. Now Gulf of Mexico seems to be still increasing, and of course the tight oil has been increasing. So we can use this decline analysis for 2 regions, for Alaska as well as for the lower 48. Now, if you look at the Alaskan production, you can see that it peaked. I drew a kind of line that it lasted around 12 years at 1.7 million barrels a day. And of course, the flow started when the Alaska pipeline was built in 1978. And then you can see where it is going to go. And the ultimate production from Alaska is going to be about 22 billion barrels. And in fact, if you use this decline analysis and draw a straight line for the data, you can see where it cuts across this horizontal axis, and that's where we get the estimate for 22 billion barrels of oil in Alaska. And then we can use the same kind of analysis for the lower 48, and you can see that it's going to end up at around 195. M. King Hubbard, who developed this technique of using this logistic equation, he predicted in 1956 already that the lower 48 is going to peak at in 1970, and it's going to have an ultimate of about 200 billion barrels. So he was pretty correct on his things. And then you get also the decline rate, both here in Alaska, 5.35, and in lower 48 like that. Then if you go to the Gulf of Mexico, this is the data. This is a monthly data, and you can see these hurricanes spikes down, and then you have this BP's big accident there, and which oil platforms burning for a number of days. And then you can separate the data based on deep water and shallow water. And I've drawn a line, that brown line, basically on the left is the shallow water. And basically, we're getting very little from the shallow water Gulf of Mexico right now. Everything comes from the deep water. And we have a kind of a peak here just before 2020. And I got information from an oil geologist who knows very well the Gulf of Mexico production, and he told that there are some new projects coming online in the next 2 years, and the question is basically, are they going to increase the production in Gulf of Mexico? Are they going to only replace what the depletion is taking place, so replacing the natural depletion out there? He doesn't think, or he kind of hedging his bets, but he doesn't think we're going to reach this 2020 high anymore. Then we come to this tight light oil, and this one also, you can see that it kind of starting to flatten out at the top. And of course, here we have the Permian Basin, which is a huge area covering north central Texas, as well as extending to New Mexico. Then we have Bakken in North Carolina. We have Niobrara in Colorado, Woodford in Oklahoma, and then these other ones are in the southern Texas, Eagle Ford and Austin Chalk, and so on. So looks like that one is already getting close to peaking. So in all, we are basically peaking in most of the world, at least in the major producing countries, and I claim, the peak in 2018, and we had now 6 years and a couple of months after. If you think that we're using 30 billion barrels a day, so 6 times that is 180, and add another couple of months there. So we have used 185 billion barrels since the peak. And as I mentioned, that this is more than the Saudi Arabia's reserve. Now, why are we using so much oil? Well, because our population is increasing. It was 1 billion around 1800, 2 billion in 2025, 3 billion in 1960, and now we have reached 8.2 billion. Now, the peak increase at 2.3% was in somewhere in 1950, a little before that, and now we are increasing at 0.9% a year. Well, there are a bunch of people in the world who are worrying about that the fertility is dropping so much that we're pretty soon we're not going to have enough people in the world. Well, I think this is not going to take place, and in fact, what's going to happen is that I don't think we're not going to reach this United Nations prediction of 10.43 billion in 2086. I think we're going to be in so much trouble long before that I think that we're going to have famines in various parts of the world. And as I keep saying, that once these fossil fuels are being used up, we're going to go back to farming by the methods of 1800s, and fertility is going to go up because families need children to help them on the farms. That's my thinking on this stuff. So the conclusions I already anticipated a little bit, and I mentioned that the technological civilization became possible by exploitation of fossil fuels, as the first slide showed. And it's completely a result of these fossil fuels. And as they start coming down, then we are in trouble. And now notice that we have burned the best fuels, and the metal ores used them up already. And So the second half is a lower quality. There's a principle called the Pareto principle after this uh, Italian economist and sociologist Pareto, who basically said that the first 80% of a task takes 20% of the effort, and the last 80% to 20% takes 80% of the effort. So this kind of goes hand in hand with the idea that, okay, we use the best part first, and it's going to be increasing difficult to get the second part out. You can think about the human society as basically a thermodynamic heat engine. And in order for it to exist in this complicated state where we are today, it requires huge amounts of material and energy flows through it. And once this flow starts to diminish, then this system is going to undergo something called a catabolic collapse. The word catabolic means it comes from chemistry, and it means that the molecules simplify. So it basically means that the society is going to simplify. First, we're going to have to give up cars, and then move to public transportation. Then you start using more bicycles and walking more and so on, and basically move into a society which existed long before that. You know, I was a youngster, entered elementary school in 1948, 49 actually. So I know the kind of life around me at that time. Nobody had private cars at the time where I came from. Now, this collapse is a necessary consequence of laws of thermodynamics. That is, once this material flows, if you think about the complexity of the world plotted in this direction, once these flows start to diminish, the complexity starts coming down, and then we hope that we're not going to come crashing down, but we're going to come down step by step. Crash is also possible, probably as a result of some new financial crisis, which is going to sink us into a period like the Great Depression. But the interesting thing about this conclusion is that after this collapse, we will never be able to produce a similar technological civilization in the future, for the reason that we have already used the best fuels and materials. So that is what I wanted to tell you, and thank you for having your attention this long. And this is something to think about and talk with your family and friends of what the future might hold. Thank you.